Hey guys, so I'm back, and this week I will be doing two things. So first off, I will be doing some of the problems from the problem sets from 2.2, and then I will be going through the notes for about half of 2.3. So we're just going to jump right in. So 2.2, in case you forgot, was dealing with, orthogonal projections, reflections, all of those types of things. So I'm just going to start off with the first question. So it was, consider a linear transformation T. Okay, we've got a transformation T from R2 to R3, right? And they want you to use T of standard vector 1 and as well as T of standard vector 2 to describe the image of n times m times 1 equals n times to describe the image of the unit square geometrically. The first thing that we should get out of the way here is if it's from R2 to R3. What does that mean? Well, that means if we've got an m times an m times 1 equals an n times 1, that means that 3 times 2, 2 times 1 leads to a 3 by 1. So now that we've got that out of the way, the way we're going to do this is, so they want us to use a standard vector. So we're going to draw, our XY plane, right? And basically what we've got here is we've got 1, 0, 0, 1, right? That's like the two standard vectors that I'm talking about. But then, sorry, I'm trying to adjust it so that you can see a little bit better. In fact, give me 1 second. Okay, I think that makes it a little bit better. But then after that, so we know now we've got 1, 0, 0, 1. We're trying to convert it onto the XYZ plane. So we know that we're going to be multiplying it by a matrix, right? And it has to be an n times m matrix, right? So that means that we're going to have x1, y1, x2, y2, x3, y3, x2, y2. And that's what we'll be multiplying each of these vectors by. We also need to point out that since we're trying to describe it with the unit square, that means that we need to add in another point right here. And that point in space is basically the addition of these two vectors. That makes sense. Because, I've already shown you that that's what happens when you add vectors in space, they come to a point. So yeah, that would be just like rounding off the unit circle. So if we multiply these two things, let's see what we get. So if you multiplied, you end up with this new vector. So you've got 0, 1 times x1, y1, x2, y2, x3, y3, and that will come out to some vector. And then you also have 1, 0 times x1, y1, 2, y2, x3, y3. And, if we think about what we know about the idea of unit squares, or the idea of standard vectors, they isolate columns, right? So this one should isolate that column, and this one should isolate that column, which means that, in other words, our new vector should be come out to be y1, y2, y3, and here x1, x2, x3. And then On top of that, we have to think about the fact that we are also going to deal with making this put in the unit circle. And if we're adding, then that means we'll have x1 plus y1 plus x2 plus y2 plus x3 plus y3 would be this point right here. And this point, of course, would be 0, 0, 0. So these would be the coordinates if we were going to put this. So we've transferred it from, this original over to here. And the thing is, like, I'm not connecting this to a plane, to any plane, because we don't know where this is on the XYZ plane. Like, we don't know, and we know it's still in the origin, because it's in the origin here. And we know from like laws that we've proved in the past that, that's going to stay the same. But we don't really know like how it's positioned, whether it's touching other parts of the axes or not. What we do know is that once it's in 3D space, is not necessarily a unit square. It's really just a unit quadrilateral. So that's just like a fact that you should know. When you convert the unit square from 2 space to 3 space, it's not necessarily a square anymore. It's any type of quadrilateral. But to like recap of what we sort of did here is we took this transformation and we used standard vectors and this unit square, and we multiplied it by, a matrix that would bring it to 3 space, and then showed the points that would result from multiplying those two things. So that's kind of just like a basic transformation. So then next video, or not next video, next problem. Okay. So, we have something that we want to interpret geometrically, and they want us to interpret t of x equals 1, 1, negative 1, 1 times x. So, or times vector x. So basically what we can do here. So we start out with our basic xy plane, right? So you have a certain vector x. And for vector x, you've got an x and a y. So to make it clear, this is our vector x. This is this line right here, and it's made up of the components of x and y. X1, I'm just gonna say x and y, horizontal, vertical, right? So we've got this vector made up of x, y. Then we're multiplying it by 1, 1, negative 1, 1, right? So if we did that, what we end up having is we've got x, y times 1, 1, negative 1, 1. Well, we would take, so based on what we know about multiplication, it would come out to be x, y, negative x, y, right? So once we know that that's the case, if this is the matrix that we end up with, we need to figure out how we're going to plot this, right? Well, that means that if this is the horizontal component and this is the vertical component, we've got negative x squared and then y squared. So for our new transformation, what we have is, well, first of all, we got to think about the fact that a negative squared is going to be positive, right? So that becomes, still stays on the positive axis, but it just squares, right? And then y does the exact same thing. We go here, but then we go here. And so our final line becomes this, right? So this is just like another example that's kind of a generic transformation. It's not really a projection or a reflection or anything like that. But to recap what we did, we have a transformation here. So we drew out X first with the two components, X and Y. We multiplied that by our transformation matrix. The matrix that we got, there should not be any multiplication signs, by the way. I sometimes throw in like additions or multiplications or whatever. When I'm doing matrices. But that's not the way that it actually works. There should not be any like pluses or minuses or anything like that within a matrix. That would be within like a systems of equations. But to recap, we've got so for the horizontal component, our final thing was X, negative X, and then Y, and that gave us our final vector. So again, both of these were just like basic taking a vector and multiplying it by a transformation matrix. And they didn't really get in too much into like those laws that we talked about with orthogonal projections or anything like that. But this next one should. So the next thing that I've got for us is a problem where, so a line in space 3 consists of all scalar multiples of vector 2, 1, 2. Okay, they want us to find the projection onto L of X. Okay, so here's what we need to think about. Our original idea of how we found this, right? Like that was given by the problem was P equals this. I'm not calling them all out because would take a long time. I'm just drawing it right here, but right, like this sort of configuration of W's is how we find the matrix for the projection. Okay, but the difference here is that this was in 2 space. This was when we were dealing with R2. We're dealing with R3. So we need to figure out what this would change to be to deal with with a 3 space. So the way that I did this was I converted it back into what we know and what we were told, which is that we also, which is that the projection, any orthogonal projection is vector X times vector U times vector U, U being a unit vector. And from there, I kind of went through some logical steps. I expanded it back out, like this time, I expanded it out the same way it was done in the notes that we went over, but instead of 2 space, 3 space. So we've got X1, X2, X3 times U1, U2, U3 times U1, U2, U3, right? So then, from there, what we can say is X1, U1 plus X2, U2 plus X3, U3 times U1, U2, U3, right? And then from there, we can finally go on to this matrix, well, actually the systems of equations that is U1 squared plus U1, U2, U1, U3, X1, U1, U2 squared. U1, U3, X3 plus U2, U3, X3 plus U3 squared, X3. Okay, so we end up with this matrix. Obviously on our matrix, I'm obviously, not going to sit here and take you through all the steps because it's pretty simple. You get from here, and then of course you isolate out all of your X's, and so you end up with this matrix U1 squared plus U1, U2, U1, U3 U1, U2 squared, U2 squared, U2, U3 squared times x1, x2, x3. So this matrix can obviously then be converted back into the W form, right? So we can convert it back into 1 over W1 squared plus W2 squared. Oh, here's where you have to not forget there's no pluses. So 1 over W1. Oh, yes, sir. So 1 over W1 squared plus W2 squared plus W3 squared times the matrix doesn't have any pluses. So let's see. So times a matrix, W1 squared, W1, W2, W1, W3, W1, W2, W2 squared, W2, W3, W1, W3, W2, W3, W3 squared, right, times 1, 1, 1, right? Because the reason that we know that is that we're told that the vector that we're dealing with is 1, 1, 1. We're told that that is, and in fact, I can find the exact moment where it tells us this, but it should be okay. So it's wanting us to find the orthogonal projection of the vector 1, 1, 1 onto L, because L, and I'll draw this out geometrically. L, as I already said, is the vector of 2, 1, 2. But we're trying to find the reflection or the orthogonal projection of 1, 1, 1 onto L, right? So that means that our vector is 1, 1, 1, and then we plug in numbers here. So our W's are going to be 2, 1, 2. So W1 is 2, W2, or sorry, W1 is 2, W2 is 1, and W3 is 2. So there, you plug all of this stuff in, you find the number that goes here, which would be 1 over 9, and you multiply it by this matrix, right? Which becomes 4, 2, 4, 2, 4, 2, 4, 2, 1, 2, 4, 2, 4. So you multiply that, and of course, then multiply it by 1, 1, 1. And the answer that you should get is 10 over 9, 5 over 9, 10 over 9. So what does this number represent? Should represent the orthogonal projection onto L, right? So that's a good example of using the projection method, and I'll remind us what we did here. So we started out knowing that we have a line in L3, and in fact, I probably shouldn't have drawn it like this. I should have drawn it on the XYZ plane. So we've got a line in R3. So it consists of all the scalar multiples of vector 2, 1, 2. So this would be line L right here, and we're trying to find vector 1, 1, 1. The line of vector 1, 1, 1 orthogonally projected onto L. So we start out with the equation that we've already been given, which is this idea of the vector x times the vector u times the vector u again. We expand that out, but this time accounting for 3 space. We go through all the steps to simplify that into this matrix times this vector. Or we go through all the steps to simplify it into this matrix times, this vector, and then turn it back into W's. The reason we don't keep it in vector U's is because, in this case, these aren't unit vectors. 2, 1, 2 is not a unit vector. If you go through the whole finding the length of it, it does not lead out to a length of 1. So we have to convert it back into this W form. And then from there, we can plug in the vector 1, 1, 1 here, and then the vector that we're orthogonally projecting onto here as W. And from there, we go through our whole multiplication process, remembering not to put any type of marks, in the matrix of like addition or subtraction, something that I'm really bad about remembering, but that can mess you up. And that's how you get the answer. So that is that one. Let's look at some others. So I'm going to end the video here because it's been kind of long, and I'm going to come back with the next one.